All right, we're in Unit 8. This is our very last unit, and it is on electrochemistry. So in electrochemistry, what we're looking at is the study of the interchange of chemical and electrical energy. That involves usually or always a redox reaction where you've got electrons being lost by a substance and electrons being gained. And of course, that transfer of electrons will lead to the production of electricity. In order for us to be able to see how electrons are transferred, we must track our changes in oxidation numbers. And so we have to understand the substance that's being oxidized and the substance that's being reduced. Loss of electrons and gain of electrons. So let's write that in. Loss of electrons versus the gaining of electrons. Okay. Now, there are two things that can happen when it comes to electrochemistry. We can either generate electricity from a spontaneous reaction, or we can use electricity to produce a non-spontaneous reaction. And recall that spontaneous reactions are reactions where the delta G is negative versus non-spontaneous. That's where delta G is positive. And we'll see the relationship between delta G and electricity later on. So I wanted to give you a brief overview of what we're getting into in this unit as we look at a chemical reaction and we see changes in their oxidation numbers resulting in electrons being transferred between two species. So we start off by looking at the reaction and we assign oxidation numbers for each given element. And when we say a given element, we're talking about hydrogen, manganese, and oxygen, and iron. Not for 4 oxygen, just a single oxygen. That's the oxidation number that we're looking at. So all single elements or atoms of a given element. If you look at this, the oxidation number of each hydrogen is a +1. Notice the positive charge here and the +1. When it comes to permanganate here, since it's an ion with a -1 charge, we have to assign oxidation numbers for each of the elements inside permanganate, leading to a -1 overall charge. So here we go. Oxygen, if you look at the periodic table, has a -2 charge. And then if you times it by 4, because there's 4 of them, is -8. -8 plus 7, so we know manganese oxidation number must be +7, gives you a -1 overall charge for permanganate. Look at iron right here, since the charge is +2, so the oxidation number is +2. The charge of manganese 2 right here is 2+, so it's 2+. So it's pretty easy when you've got it singular. A given element is by itself as a singular atom. So it's just +3. Now when it's a compound, you do have to assign each of the elements inside that compound, or atoms of that, each of the inside the compound. So oxygen, once again, is -2, giving us 2 hydrogens, so each one is +1. So these are the singular oxidation numbers for each of the elements that we see here. For hydrogen here, for manganese, for oxygen, each oxygen is -2. Iron 2+, manganese 2+, iron 3+. Each hydrogen is 1+. Each oxygen, which there is only one here, is -2. So we see changes in oxidation numbers. Now, what changes do we see? Well, the word reduction means the oxidation number has reduced. So reduce means it decreased in value. So if you look at manganese oxidation number actually decreased to manganese 2+. Likewise, over here, iron, or opposingly, actually not likewise, oppositely, iron 2+ increase in oxidation number to iron 3+, which means iron 2+ has lost electrons. That's why it becomes more positive in terms of the charge here. So that's your 2 oxidation and reduction reaction. So we like to split this up because in order for us to see electricity go from one species to the next, what we tend to do is split up into half reactions. So the oxidation half reaction is the following. It is taking the iron 2 plus and becomes iron 3 plus. Now how that could happen is, if you notice the charge is a plus 2 to a 3 plus. That means one electron was lost in this exchange. Now we go to manganese. So manganese was a 7 plus charge, and then it gained 5 electrons. Let me explain where that 5 comes from, to become manganese 2 plus. Now where that 5 comes from is when you go from a 7 plus 7 oxidation number to a plus 2, you must have gained 5 electrons to do so. And notice electrons are negative, so a negative 5 plus a positive 7 gives you a positive 2 charge. So 5 electrons were gained. Now if you look at this reaction, you'll notice that the electrons don't match up. There's 5 here, or 1 electron here, and 5 electrons here. So you have to match them up in terms of showing the conservation of that idea that electrons lost, the same number, is going to be the same number of electrons gained. So what I'm going to have to do is I'm going to have to multiply this reaction by 5. Upon multiplying by 5, everything gets multiplied in and distribute in. And I tend to like to rewrite this equation with the distribution of that 5 into the equation. As a result, the overall equation is going to look like this. It's going to be 5 iron 2 plus, and I'll write the coefficients later. But ultimately, you'll notice that the 5 electrons cancels out, and that's why you don't see electrons in a redox reaction. It tends to go away because they cancel in the end, leaving us with iron 3 plus and manganese 2 plus. So the coefficients are the following. I'll put it in red. So 5 here, 1 here, 5 here, and 1 here. And that is our balanced redox reaction. Notice how it really matches up to what you see here as far as manganese is 1. There's only 1 manganese 7 plus. There's 5 iron 2 plus. And then, of course, manganese 2 plus, there's only 1, as we see right here. And there's 5 iron 3 plus right here. So this is our half reactions. And the really important part of doing this is to understand that there were 5 electrons transferred between the manganese 7 plus to that of the the iron 3 plus or 2 plus to, so I'll refresh this. The 5 iron 2 plus is going to transfer those 5 electrons to the 1 manganese 7 plus. So that's the important part of writing half reactions, because we actually can trace out how the electrons are flowing and who's losing the electrons versus who's gaining. So the loss of electrons is called the half reaction oxidation. The gain of electrons is called the reduction half reaction. And of course, the overall is just the addition of the 2 reactions. So how does a redox reaction generate electricity? In the previous example, if manganese, permanganate, and iron 2 plus are present together in the same solution, the 5 electrons are actually transferred directly upon collision. This is not productive because the energy generated is lost as heat, so we must separate the permanganate, which is the oxidizing agent, from the iron 2 plus, which is the reducing agent. The separation forces the electrons to transfer from the iron 2 plus to the permanganate, which has the manganese 7 plus, to occur through an external wire. So what we do is we basically put two beakers here, and we put all the species needed in one side of the electrode, and then on the opposite side is the other electrode. So this is basically oxidation on one side and then reduction on the other side. And that way the electrons can flow through this external wire, which then can be measured by a voltmeter as far as how much electrical output will be provided given this reaction, and the species and the amounts of the species that are in each of these electrodes, or the cathode or the anode. Okay, so this is called a galvanic cell, and it's an electrochemical cell. So usually this is a spontaneous reaction that's coming out of this setup here. There's something also called a salt bridge, which will play a very important role in creating this battery right here, made up of a chemical reaction that's occurring. Okay, so that's a brief little overview of electrochemistry. We're going to dive into it even more so later on. But let's practice oxidation numbers. What is oxidation numbers? There's really no physical meaning to oxidation numbers, but I've come down to a pretty good definition for it, and that's the valence electrons involved in bonding, including covalent and ionic bonding. So let me go ahead and contrast ionic bonding versus covalent bonding, and we can see how oxidation numbers work. For ionic compounds, oxidation numbers are actually the charges on the ions. For covalent compounds, oxidation numbers are the number of valence electrons shared with other atoms illustrated in the Lewis structure. So let's take a look down here. Here we see manganese bonded to two chlorine atoms, but they're actually going to ionize. So manganese is going to lose its 2 valence electron in order to have a full energy level and be isoelectronic with neon. Chlorine is going to each gain 1 electron. Upon gaining 1 electron, both are going to be isoelectronic with argon, having a full shell. Now, with the transfer of electrons within this species, the oxidation numbers are the following. Manganese now has a 2 plus charge. Each chlorine has a -1 charge. And so these are the oxidation numbers showing the electrons that are lost, involved in bond, to be bonded, and then of course the electrons that are gained by the chlorine atoms, thus the 1 electron gained by each of the chlorine atoms, thus the oxidation number is -1. Now, this is no different for covalent. Now, if you look at covalent, the oxygen is sharing 2 electrons. So the oxidation number is a -2. Hydrogen is sharing 1 electron. So this is the 1 electron involved in bonding. So that's why its oxidation number is +1 for each one of these. You still want to neutralize these oxidation numbers to see that overall this water molecule is going to be neutral in terms of these oxidation numbers. Likewise, over here, you're trying to achieve electroneutrality, and so these charges on these ions have to be also neutral in the end. So let's go ahead and summarize what was happening between the ionic bonding versus covalent bonding. In the ionic bonding, how many of magnesium's valence electrons were involved in bonding? In other words, lost. And we know that there were 2 electrons lost. So the oxidation number, as we see it, was +2. How many of chlorine's valence electrons were involved in bonding? Only 1 electron was involved in bonding, and so the oxidation number is a -1 for each of the chlorine atoms. Now, of course, we had to times 2 that because there's 2 of them, thus a -2 overall charge. But the oxidation number is still -1 for each chlorine, as it is for each magnesium is +2. Now let's go over to water. How many of oxygen's and hydrogen's valence electrons were involved in bonding? So we saw in oxygen that 2 of them were involved in bonding. So the oxidation number of oxygen is actually -2. And of course, hydrogen, only one of hydrogen was involved in bonding, so the oxidation number is +1. So hopefully you can see the oxidation numbers for each of the elements that are in there. What I would like to do is give you some set of rules that we want to make sure that you follow when it comes to oxidation numbers. You want to assign for a single atom of a given element, giving oftentimes the more electronegative and negative charge, while the electropositive atom is positively charged. So once again, in water, you'll notice that water has hydrogen and oxygen. Hydrogen is +1, oxygen is -1 because oxygen is more electronegative than hydrogen. Assign the oxidation number for elements you know first, like groups 1 and 2. For example, the oxidation of sodium is +1, but iron is difficult because it has various oxidation numbers. It's in the D block. And D block elements have varying oxidation numbers and charges. Oxygen is almost always a -2 unless it's peroxide. Notice if it was peroxide, like you see O22- here, you'll notice that oxygen actually takes on a -1 in order for 2 of them to be a -2. So that's why you watch out for peroxide, which is O22-. Free elements have an oxidation number of 0. So if you take a look at all these free elements, now some of them are diatomic, so be careful. The diatomic ones are free elements, and they like to exist diatomically because otherwise they wouldn't exist. They wouldn't be stable to exist. So all of these have an oxidation number of 0. The sum of all the oxidation numbers add up to the overall charge of the whole compound. At times, draw the Lewis structure for covalent compounds to be sure of the assigned oxidation number. So let's go ahead and assign the oxidation numbers of these substances. We do want to name them also because the direction says to name and assign oxidation numbers. So let's start off with this. This substance right here looks like uranium and fluorine. And so I'm going to call it uranium fluoride. Okay, so now I assign oxidation number for the elements that I know for sure more. And I do know my halogens. My halogen has an oxidation number of -1. And so I'm going to put -1 as my oxidation number. Now, since there's 6 of them, uranium has to be a +6 in order to neutralize that compound and to have an overall charge of 0. There's no charge here, so the overall charge has to be 0. So this must be a +6. Once again, let's look at the next substance. The next substance is, let's name it. It looks like an acid. So it has sulfate, so the 8 with the ick, ite with the us, so this is called sulfuric acid. And playing around with this, sulfuric acid. Okay. Now, once again, I go with what I know. I know that this is -2. Hydrogen is +1. Now, sulfur, since it lays in the middle of that periodic table, anything in the middle tends to have varying oxidation numbers, so you just do some charge balancing. In other words, -2, you times that by 4, because there's 4 of them right here, 4 of them, gives us -8 overall. So this is -8. Hydrogen times 2 gives us +2. So -8, +2. What must sulfur be in order to neutralize these charges? So you're right to say plus 6, because plus 6 gives us an overall charge of 0. So the oxidation number of sulfur is plus 6. So the next compound, once again, looking at the substance, this is a polyatomic ion, and that is chlorate. Assigning oxidation numbers, I'm going to go with oxygen. I know it's -2, always -2, pretty easy. But then I need to be able to account for the -1 overall charge that I have to have for chlorate ion here. So once again, I do a little bit of algebra. Times this by 3 gives me -6. -6 plus what gives me -1? And you're right to say +5, because -6 plus +5 gives us -1. So the oxidation number of chlorine in chlorate is +5. Go ahead and look at the next one. This substance looks like it's sodium chromate. You're practicing your naming systems. Oxygen. Now, I know sodium's oxidation number is pretty easy, so it is +1 since it's group 1. Group 1 elements are always +1. Oxygen is -2. And so chromium is in the middle of the periodic table. It varies in terms of its oxidation number, so we're going to have to work our way to figure out what would charge balance this whole compound. So there's 2 of these. That means it's +2. There are 4 of these, which means it's -8. So what must neutralize these charges here? And you're right to say +6. +6 will neutralize this charge. So the oxidation number of chromium is +6. Let's look at the last one together. The rest you'll do on your own and practice. Obviously, the answer key is all there for you. Please make sure you're practicing, though. Now for letter E. In letter E, we have iodine becoming iodide. So let's go ahead and write that in. We have iodine becoming iodide. So that's the ion part. Now, the oxidation numbers, if you notice, for I2, it's a free element. And we said that free elements all have an oxidation number of 0. So we're going to write 0 in for iodine. And then -1, as you can see right off the bat, for iodide. Go ahead and work through the rest from F through J. Now let's go ahead and go to the next section, which is an introduction to oxidation reduction. One thing that I like to use is this acronym called Leo-Says-Gur. Leo stands for lose electrons, oxidation, gain electrons, reduction. So Leo-Says-Gur helps us to know what's happening to the oxidation portion versus the reduction portion. The first thing you want to do is assign oxidation numbers for a chemical reaction, so you can see how the oxidation numbers change. And so the oxidation number for magnesium is 0 here, +1, -1, +2, -1, and 0. So you'll notice that magnesium changes its oxidation number from 0 to +2, which means the oxidation number increased. That increase means that magnesium has been oxidized, and thus it's called the reducing agent. So what's oxidized is in fact the agent that is helping in the reduction, so that's why we call it the reducing agent also. So oxidized and reducing agent are basically the same species. However, the agents are going to be the whole substance that that element or that atom that has been reduced or oxidized contains. So oxidation is the loss of electrons. The oxidation number increases as we see here. 0 to plus 2 means the oxidation number has increased. Now we go to reduction. If you notice, tracking your oxidation numbers, you'll notice that hydrogen goes from a +1 to a 0. And that means hydrogen has been reduced, hydrogen ion has been reduced, and the whole substance that hydrogen ion is contained in is the oxidizing agent. So HCl is the oxidizing agent. What we're going to do in example 3 is we're going to practice this using the same idea. We're assigning oxidation numbers, and then we're going to see who's oxidized and who's reduced. We're also going to identify the oxidizing agent and the reducing agent, and we're going to figure out how many electrons are transferred. If the reaction is not redox, go ahead and say no, not a redox. Let's go ahead and look at the first letter A from example 3. In A, we assign oxidation numbers. Calcium has an oxidation number +2. Chlorine, each chlorine is -1, 0, 0. I'm going to start off with O, and then I'm going to also, O is what's oxidized, R is what's reduced, and then of course RA is the reducing agent, OA is the oxidizing agent. So we're going to identify each one, okay? So who is being oxidized? So I'm looking for an increase in oxidation numbers for what is oxidized. And chlorine goes from -1 to 0, which means chloride ion is being oxidized. And I'm going to write it in black. So Cl minus is being oxidized, so losing electrons. Who gained it? Well, calcium 2+ gained those electrons. That's why its oxidation number goes down. So reduce. So that's why the word reduction comes about. So oxidation number goes from +2 to 0. So that's a reduction in oxidation number. Now, what is the reducing agent? Well, the reducing agent is that in which is oxidized, chloride ion. But the whole substance that chloride ion is contained in is what we identify as the reducing agent. So it's calcium chloride. Likewise, calcium 2+ is what's being reduced, and where that substance came from, the whole substance is calcium chloride. So the same substance that is oxidized, or the reducing agent, is also the oxidizing agent. And this really does make sense in the sense that what better way than to have the same substance that's in, or the elements that are in that substance transfer electrons between the two species. They're next door to each other. Why wouldn't it be convenient for those electrons to easily transfer when they're right next door and bonded together like it is here? So let's go ahead and look at the next one, B, letter B. We'll do a few of these together and then you're on your own after that. So once again, oxidation numbers is what I'm going to assign. I'm going to assign it on top so I have a little room. +2, -2, -2 times 3, -6, +6. +2, -2, 4, -2 times 4 is -8, plus, okay, so this is +6. So we're looking for any changes in oxidation numbers. We're going to map out which ones are each. So we're going to do oxidized versus reduced. And then since it's oxidized, it's also the reducing agent. And then since it's reduced, it's the oxidizing agent. So I'll line it up exactly together like this. What's oxidized is the reducing agent. What's reduced is the oxidizing agent. Looking at the oxidation number, calcium doesn't change. Calcium ion, 2+ ions do not change in oxidation numbers, so it's not involved in the redox reaction. Oxygen is also not involved as well because it's going from a -2 here and -2 here, and it's still -2. So, and then we look at sulfur. Sulfur also doesn't undergo a change. So in essence, there's no redox. This is not a redox reaction. So this is an example of why you have to always track your oxidation numbers to see if it's a redox. Okay, let's do the last one. Once again, I'm just going to set myself up. O-R-R-A, reducing agent, oxidizing agent. Okay, so assigning oxidation numbers, this is 0, free element, plus 1, and minus 3. Okay, so it looks like lithium goes from a 0 to a plus 1, which means its oxidation number increase, which means it's oxidized. So lithium has been oxidized. And of course, the reducing agent is the whole substance, which is lithium. So the whole substance is lithium, so it's Li. Now we go to what's reduce. So who's gaining electrons? If we look at nitrogen, it goes from a 0 to a minus 3 oxidation number, which means nitrogen has gained electrons. How many electrons are gained? We'll figure out the number of electrons later. I forgot to do that. So it's N2 is what is reduced, and N2 is also the oxidizing agent. I did forget to trace the electrons. I'll go back up to letter A and do the electrons, and I'll do it in blue or yellow. So if calcium goes from a plus 2 to a 0, and there's only one of each here, that means calcium gained 2 electrons. So there's going from here to here, there's a gaining of 2 electrons. Likewise over here, chlorine goes from here to here, and that means each chlorine atom gained 1 electron, but there's twice, so times it by 2. So that's where the 2 electrons lost, 2 electrons gained means there's 2 electrons transferred. Okay, let's go to the next one. So lithium goes from here to a plus 1 charge here. So that means lithium lost 1. So there's a loss of 1 electron, but there's 6 of them. So there's times that by 6. So there's 6 electrons lost. And then, of course, each nitrogen, look at it carefully, each nitrogen goes from 0 to a negative 3. So each nitrogen gains 3 electrons. There's 2 of them, 2 of them right here. So that's times 2. So once again, moving to the nitrogen, each one gains 3 electrons. Times that by 2 gives you 6 electrons. So really, 6 electrons transferred. Okay. Go ahead and work through D and E and F. Answers are on the bottom, so you can double check to make sure you're doing it right as I've shown you how to do a few. Go ahead to unpause afterwards and let's look at standard reduction table. So this is a standard reduction table. Now, how is it? Let's look at the word standard reduction, okay? Standard means we're at 25 degrees Celsius and 1 atm of pressure and 1 molar solutions, if there are solutions. Reduction means you're adding electrons, so you're gaining electrons. So you're going to see these substances look like this in form. You're gaining an electron, an element of some sort. Sometimes there's different charges, of course, so we do have to balance out those charges. So it's in reduction format. And you'll notice that electrons are being gained on one side or on the left side, forming whatever species it is on the right-hand side. What substance is at the top of the standard reduction table? Let's take a look at the top. Looks like it's fluorine. Well, we know fluorine is a halogen, and it's one shy of having a full shell, so it makes sense that fluorine really would like to gain an electron, so it has a very high reduction potential. So fluorine is at the top. And of course, we know it's a halogen with 7 valence electrons. And those 7 electrons encourages that substance to really want to gain, and wants to gain one electron in order to have a full shell. And so that's why you see fluorine at the top of the reduction table. Now, what's at the bottom of the reduction table? Well, at the bottom is lithium right here, lithium ion. This is trying to get you to think about the logic of why, who's on top and who's on bottom, and why it's the case. Now, I'll explain why. Well, lithium is going to be a very poor substance to want to gain electrons. Lithium, on the other hand, really would like to lose electrons. I'll say it's in the same form, is an alkali metal. And in that, alkali metals tend to lose one electron. And so you're really seeing one on the top of the reduction table are your elements that really want to gain. On the bottom of your reduction table are your elements that want to lose electrons. And that's why you're seeing these substances be strong oxidizers, these substances being strong reducers. Okay? Now, the stronger the reducer, the weaker the oxidizer. So we know if it gains electrons easily, it's going to be poor at losing electrons. So the weaker the oxidizer. Let's see which one is stronger oxidizing agent. Now, the stronger oxidizing agent is the one that gains an electron easily. Who gains an electron easily between these two elements? You can either look it up on the chart and you can see who gains the electrons easily. Here is iron right here, iron solid, and here is iron 3+. And it looks like iron 3+ is higher up here, which means it's better at gaining an electron. And more than that, you can actually look at the structure to understand why iron 3+ is more likely to gain. It's got a positive 3+ charge. This one's neutral. Positive 3 means it would love to gain and neutralize itself. So you're seeing this substance really gain an electron a lot easier than iron neutral. Which one is a stronger reducing agent? Reducing agent is a substance that is oxidized. So which one loses an electron easily? Well, fluorine doesn't want to lose an electron. It actually wants to gain. That's why it's up here. Fluorine is better at gaining, reducing, than it is losing. So who is the better oxidizer? It is sodium. Sodium's down right, should be down here. Okay, right here. So sodium is better at losing electrons. So I'm going to circle this. So when it comes to the agents, I like to think of whatever. So a strong oxidizing agent would be something that is easily reduced. A stronger reducing agent is something that easily oxidizes. Go ahead and work through some of these examples as you've seen me work through some of these. And then check your answers in the very back to make sure you understand what you've circled as stronger oxidizing agents and why. Okay? Now we get into half reactions and being able to split up a whole reaction into half reactions of oxidation and reduction. There's this ABC kind of acronym to help you to balance half reactions or balance redox reactions with these half reaction method. Now, you don't really have to memorize this, honestly. It becomes intuitive after you've balanced enough. So the first thing you want to do is assign oxidation numbers. And I'll go ahead and assign oxidation numbers. You should be pretty good at this point. And then what you do is you see who's being oxidized and who's reduced. So since magnesium goes from a 0 to a +2 charge, that means magnesium has lost 2 electrons. Hydrogen goes from a +1 to a 0 charge, and so hydrogen has gained 1 electron each. Now, of course, this is not balanced yet, so now we're going to balance the atoms so we can see how the electrons are, how many electrons. So I'm going to balance the atoms. Upon balancing the atoms, I'll notice that everything is a 1 coefficient except for the hydrochloric acid. So 1, 1, 1, 1. I'll do that again. 2, 1, 1. Now, then what we do is balance the charges on each side using the half reaction method. And so I'm going to go ahead and go to this chart and split each of the half. We said that magnesium has lost electrons, so it goes from Mg solid to Mg2+, and that means it lost 2 electrons. Hydrogen ion has gained electrons, and so since hydrogen has gained electrons, we are going to write H+ ions and a certain amount of electrons, it's 1 electron, forming H2. Now, since there's 2 of them, that means there's 2 electrons that are gained, and I do have to conserve my mass. There's 2 hydrogens here, so there's 2 hydrogen ions here. And each hydrogen ion is going to gain 1 electron. There's 2 of them, so there's 2 electrons gained total. And then what I do is I add up each of this. Since the electrons cancel themselves out, which is nice, we then add both half reactions to make what is called our whole reaction. So this is magnesium solid, 2 hydrogen ions aqueous, forming magnesium ions aqueous and H2 gas. Okay. Go ahead and work through the rest. I do want to point out, notice how in the balance equation you're seeing everything conserve. Here's 1 magnesium. There's 2 hydrogen ions, thus 2 hydrogen ions, and then 1 magnesium 2+ and a hydrogen diatomic molecule here. So now what happened to the chloride ion? The chloride ion is a spectator ion. You'll notice that its oxidation number, chloride's oxidation number, didn't change between the reactants and products. And so I've eliminated the spectator ion and have what is called the net ionic equation. So this is my net ionic equation. You tend to yield your net ionic once you get rid of your spectator ions. Let's do another one. So assigning oxidation numbers, I'm going to assign it above here. So +2, 0, +2, +3, 0, +2, and +2. So if you look at the oxidation numbers, cobalt goes from a +3 to a +2, so reduce. That means I'm going to go to the reduction half reaction. So this is going to be my half reaction reduction. This is my half reaction oxidation, okay? So in my reduction, I'm going to write cobalt 3+, gaining 1 electron to form cobalt 2+. And then who has been oxidized? Nickel. Goes from 0 to nickel 2+. And there's 2 electrons lost as a result. Now, since the electrons don't equalize, in other words, there's 2 electrons lost here and 1 electron gain, what we have to do is we have to equalize it. Find the greatest common multiple between the two, and that is 2. So we're going to have to take this equation and multiply it times 2. Now, I really do like to distribute that 2 into the whole equation. So I'm actually going to put 2 here and 2 here. I really do like distributing, so I don't forget to put those coefficients. So the whole reaction, when I add them together, the half reactions, yield the following. I have nickel plus 2 cobalt 3 plus ions. And of course, the electrons cancel themselves out. You don't see those electrons in a redox reaction, but doing this half reaction method, you actually see how many electrons are transferred. And that's why we like this. We like to write the half reactions. And then this is cobalt 2 plus. And so this is the balanced equation. I'm going to go up to here and write the coefficients are 1 for the nickel, as we see here, 1, 2 for the cobalt 3 plus, 1 for the nickel 2 plus, and 2 for the cobalt 2 plus. So I'm going to go ahead and go to the original equation, which is up here, and just write 2, 1, 1, 2. So you should see conservation of mass, as always, in this balanced equation. Go ahead and work through the rest of the problems and check your answers as you go through the rest of these problems. Okay. Now we get into standard cell potential and electrochemical cells. We're going to actually take these half reactions and separate them into literally half reactions. And when we do that, we can actually calculate how much voltage there would be between those 2 half reactions. You're going to need to scan and make sure you bring up the standard reduction table here. So go ahead and scan. Note that all you do is you sum up the reduction potential and the oxidation potential. You flip the reaction. Flipping the reaction will yield the opposite sign for the voltage. However, multiplying the reaction will not result in changes to the voltage, as it's independent of the amount. That's why you don't see the per mole like you do in Gibbs free energy or enthalpy or entropy. So this is an independent, we call it an intrinsic property. Cell potential is an intrinsic property rather than an extrinsic property. So what we do is we look at the voltage values. So scan this, and we see that, once you scan it, you look for magnesium, and you'll see magnesium to be in a reduction format, which means these products are actually in the reactants and these reactants are in the products. So in order for me to flip that reaction, I am going to take the opposite sign, as it says right here. Flipping the reaction will yield the opposite sign, and that's what I've done here. Now, here's the reduction half reaction, and it's written as is, and the voltage is 0. It actually is the standard reduction value potential. And when I add up these two, all you do is you get your net overall voltage. So these 2 half reactions will yield a voltage of 2.34 volts. And it's electrical energy, so we are interested in measuring this electrical output from this chemical reaction. I went back to 5 and A. So 5A, B, C, D, E. I did provide one of the values for E because you can find it on the reduction potential table. So the first thing you want to do is find the cell potential for each of these half reactions. Scan the QR code and get the standard reduction potential table up. And when you do that, find nickel going to nickel 2 plus, neutral nickel going to nickel 2 plus 2 electrons. Now, obviously, it's the reduction table, but since you flipped that reduction to make this oxidation half reaction, you're going to have to flip the sign. So whatever that value for nickel is, which I found out to be negative 0.25, you're going to take the opposite of that value in the end. And then I'm going to look for the cobalt. Cobalt's right on top. And the value that cobalt has is 1.82. And you don't need to flip it because it's in the reduction form as the table is written in. And so what you do is you just add up those half reactions and you get the overall cell voltage. So it ends up being, and I'll use my calculator, 2.07 volts. Go ahead and work through the rest of the problems from B all the way through E. Again, I provided one of the values because it's not on your reduction table. And check your answer key. Let's go into galvanic, voltaic, electrochemical, and Daniell cells. All these cells are really spontaneous, basically. It's a device in which chemical energy from a spontaneous redox reaction is changed to electrical that can be used to do work. The components of these cells, you can actually call them voltaic. It's an old term for it, but it's galvanic we use today, are an anode, a cathode, a voltmeter, and there's also a salt bridge. So these are the main components of a galvanic cell. And the anode is where the oxidation half reaction occurs, and that's the metal electrode that's losing electrons. The cathode is the electrode, the metal electrode, where you're gaining electrons. So there's a mistake here. So it should be gaining electrons. And that's where the reduction half reaction occurs. And also the reducing agent is also in the original substance that contains the substance that gains electrons. The voltmeter is going to be where the electrical wire is. It's a device that measures the electrical energy as the chemical redox reaction occurs. And it's measured in volts, which is joules per coulomb. The salt bridge is a semi-permeable membrane that permits ions to flow back and forth, and it really does replenish the ions due to culminating charges without allowing excessive or extensive mixing of the two solutions. And the salt bridge, without the salt bridge, electricity, the electrical current would not flow because there's no circuit, and a buildup of negative charges at the cathode would occur. Thus, there would be no electricity flowing. I do want to make sure you understand the notation. They made a notation for these galvanic cells, and the notation is such that the anode is on the left, cathode on the right, and of course in the middle is this parallel lines, which represents the salt bridge. The anode is made up of the electrode right here, which is zinc, and then of course the solution of ions that are a certain concentration that's in the anode cell. The cathode side is made up of the electrode that will gain electrons to become the metal electrode that you see here. And this is a format and notation, it's called the line notation, that allows us to be able to format our cells, our electrochemical cells. Another way to also do this is without the spectator ions. So the nitrates are in each of the beakers on both the anode and the cathode, but they're spectator ions. So because they're spectator ions, we eliminate them, and this is how we also can format this electrochemical cells. All right, the first thing we want to do is look at the half reactions, understanding where we're getting all these values between zinc and copper 2+ ions. and the transfer of electrons, 2 electrons specifically between the two species, to form zinc 2 plus and copper neutral here. This reaction is spontaneous. And we know it's spontaneous because of this relationship right here. The relationship is in this equation right here on your equation sheet. And if E is positive, you'll see that that negative will allow the G to be a negative value. So E positive leads to a spontaneous reaction. E negative leads to a non-spontaneous reaction, because a negative of a negative gives you a positive, and delta G positive means it's non-spontaneous. So we can actually see the relationship between the sign of the cell potential overall and its spontaneity of the reaction. Let's take a look at this and explore this reaction. So we know the oxidation half reaction is where the anode is taking place. And the way I remember this is I see the word A and anode is vowel. Likewise, oxidation starts off with the vowel. Consonant, C. Reduction starts with a consonant. Ultimately, eventually, you'll see the it'll be habit forming that you'll know the anode is oxidation half reaction. So zinc becomes zinc 2 plus ions, losing 2 electrons. And where you're going to get the zinc is right here. This is where the zinc substance is. And I'll put it in red. This is zinc, solid. Now, where you're going to get the copper on the opposite. So as a result of the zinc losing electrons, that zinc gets, the ions will leach out into the solution to make zinc 2 plus ions here. Over here, in this half reaction, you need copper ions will gain, so electrons are going to flow through here, and I'll show the electrons flowing as zinc loses 2 electrons through in this direction. And of course, those electrons are going to draw the copper 2 plus ions that are in solution. Now 2 plus means it's positive charge, electrons are negative. It's going to draw those copper 2 plus ions to the electrode, the copper electrode. So Cu2 plus is going to be drawn over here and gaining 2 electrons, and thus you're going to see copper forming, copper solid. So you'll actually see mass increase here, and then you're going to see this eroding, so the mass decrease here. And that's why you see a loss of mass, thus a gaining of mass on one side. You'll literally see in the electrode accumulation of copper and then the erosion of this zinc electrode. And these are metals, by the way. The electrodes are, this is zinc, this is solid zinc, and this is solid copper. And the electrons will continue on. So let's talk about the role of the salt bridge. As you're getting more positive here, as zinc solid becomes zinc 2 plus ions, so the solution is becoming more positive. And then as you're losing the positive, so that copper 2 plus becomes neutral copper over here in this electrode, this side is getting more positive, this side is getting more negative. So the salt bridge is really important, because if we don't have the salt bridge, the accumulation of charges will prevent electrons from wanting to flow over to here, over to the cathode side, if it's getting more negative over to here on this side. Why would electrons being negatively charged want to go to a side that's more negative? It wouldn't. So the salt bridge is made up of this saturated solution of potassium nitrate, and potassium nitrate has 2 components to it. It's made up of potassium ions and nitrate ions. So those 2 ions are really important for us to replenish the charges that we see. Now, where will charges, which ion will go where? Now, since over here on the cathode side, you're getting more, you're losing that positive, which means you're getting more negative. That means the potassium is going to want to move down here to replenish the loss of that positive charge as copper 2 plus becomes neutral copper. Over here, since you're becoming more positive due to the zinc 2 plus ions that are leaching out in the solution, you want a negative ion. And the negative ion that will help to replenish and prevent this side to be, the anode side to be more positive, is the nitrate ion. So you're really trying to help replenish charges so that the circuit can continue, the electrons can continue to flow. Without the salt bridge, you wouldn't be able to see the electrons will flow initially, but then it'll stop because there's so much accumulation of negative charges here and then positive charges here, which prevents electrons from flowing easily into the cathode. All right, let's go ahead. And by the way, the reading right here is going to show a voltage of, as we see in our half reaction chart, 1.10 volts. So this is what's the output reading of the voltage for this particular galvanic cell. Let's go ahead and look at example number 7. In example number 7, we are looking at calculating the standard cell potential using the table information in the table below. Now, I'm in a pause the video so I can draw in the table, but there's missing a table currently, and I'll put that in once you unpause. This is the missing table, and there's also a quick little assumption that is missing out of this question, and that the reaction is spontaneous, which means your E is going to be a positive E. So irregardless of what you do, you need to make your E positive. The only way you can make your E positive is if this becomes a negative value. Now, how this becomes a negative value is if you were to flip this reaction. Let's go ahead and assign oxidation numbers. 0 becomes -1. This is positive 5, -2, positive 1, 0, positive 1, -2. So we can tell that in this reaction that this bromine will gain electrons. And how many electrons you'll gain is for each bromine will gain 5 electrons. And how I know this is because I see the oxidation number changing by 5. Now there's obviously 2, so I'm going to have to account for the 2 by putting a coefficient of 2 right here. I'm just really strictly balancing. So that 2 will yield really 10 electrons. So I'm going to change that to 10 electrons that are exchanged. In this case, the same thing here, where I'm looking at the oxidation number of a single bromine. It gained lost 1 electron. Upon losing, there's 2 of them, so there's 2 electrons lost in total. Now, do the electrons, obviously I'm going to flip this reaction. I'm actually going to do that right now below. In flipping this reaction, I'm also going to multiply this reaction times 5. Well, why? Well, because there's 10 electrons right here, and there's only 2, so the common multiple is 10, which means I'm going to have to multiply this reaction by 5 as well as I'm going to flip it. So I'm going to do both at the same time, okay? And in doing both at the same time, this is what I get. I get bromine or bromide. And 5 of them, so 5 times that, or 10 times that, 10. Going to forming 5 Br2 plus 10 electrons. And the flip of that reaction is going to lead me to 1.6065. Now, adding these two reactions together, just adding these two, you'll see that electrons are going to cancel themselves out as they should, and you're left with the net being this right here when you add those two half reactions. And adding the 2 voltage value, you should get the final voltage value that is 0.45 volts in the end. And this reaction is in fact spontaneous because E is greater than 0. So we know that this reaction does hold true to the condition that we set, which is assume this reaction is spontaneous. Now, how many electrons are transferred? And we can see it. We can track that there's 10 total electrons transferred. And of course, the overall balance equation is just adding these two half reactions to get this overall balanced equation right here. Now, once we see this overall balanced equation, though, we see that there's a reduction that can happen. That reduction is you can reduce it by 2, and dividing by 2 gives us an even the lowest whole number ratio for this balanced equation. Let's explore the relationship between KEQ, Gibbs free energy, change in Gibbs free energy, so equilibrium, change in Gibbs free energy, and self potential. So they're actually related through these 3 equations that we see on our reference sheet. So be familiar with them and know that they are related, they link one another to each other, okay? And so this is a little triangle to show that dynamic relationship. The 3 equations are listed also right here. There's standard conditions versus non-standard conditions. We're not using the word equilibrium. This is standard versus non-standard conditions. Now, when we talk about standard conditions, we're talking about 25 degrees Celsius as far as temperature, 1 molar solutions as far as the concentrations of all the solutions, and then also 1 atm pressure. In this, we're going to need to familiarize ourselves with F and N. N in this case is the moles of electrons transferred. F is Faraday's constant. What this will allow us to help us to understand is depending on the number of electrons transferred in a chemical reaction, we can actually determine the cell voltage based on the equilibrium conditions and concentrations of our ions. This chart is really important for us to understand how the dynamic of the reaction is going to depend on the concentration at standard conditions or not standard conditions. So the word thermodynamically favorable, and we actually are looking at all these reactions in the forward direction. So in the forward direction, when you're thermodynamically favorable, what that means is the reaction is negative in the forward direction as far as Gibbs free energy. So that means it's spontaneous in the forward direction. And of course, the E cell is positive. And we know that if you have a negative value right here, E cell must be positive. When that happens, that means your Q is greater than your K because there are the reactions favoring the formation of products over the reactants. When you have a thermodynamically unfavorable reaction in the forward direction, that means the Gibbs free energy is negative. E cell is going to be less than 0. G is positive, which means it's non-spontaneous, and then the E cell is less than 0. And in this case, your Q is actually going to be less than your K, which means you have a lot more reactants than products. So it doesn't favor the production of products at that point. Now, when you're neither thermodynamically favorable nor unfavorable in that forward direction, aka you're at equilibrium, that means your G is equal to 0, which means chemical equilibrium. That means your E also must be equal to 0. E0 means G0. And that's when your Q is in the condition of your K, so it's equal to K, so you're at equilibrium. The Nernst equation will help us to understand the relationship between the cell potential and the concentrations of the cell components, which we can calculate through Q. Let me make sure we understand Faraday's constant. The charge on a mole of electron is called Faraday's constant. And to understand that there's this many charge for each mole of electron, or for each electron, and if you have a mole of electrons, which is 6.022 times 10 to the 23rd, for each electron to hold this much charge in coulombs, that means if I multiply these two, that will tell me how much charge per 1 mole of electron. And this is how Faraday's constant is derived. It's understanding how much charge per electron, thus a mole of that is going to be times 6.022 times 10 to the 23rd. And that's where we get this Faraday's constant value that you see up here. This represents how much charge carried by a mole of electrons. Let's review the y equals ln of x graph. When x is greater than 1 is our reference, you see that your output, which is y, is going to be a positive value. When x is less than 1, you're going to see the output to be a negative y value. And then, of course, when it's equal to 1, you see the y is going to be 0. And so this follows through with this equation right here, the Nernst equation, where the ln of anything greater than 1 is going to give you a positive value. Equal to 1 gives you ln of q that is equal to 0. And then less than 1, ln of q is going to be less than 0, which is a negative value. Now, how does that help us? What does that mean for us? What allows us to compare non-standard versus standard conditions for your E cell, and how changing the Q concentration, so the non-standard conditions will change your E cell relative to your E cell standard. If my LNQ is greater than 1, what happens is this is going to give me a positive value. That positive value subtracted from your E cell standard is going to give you an E cell that is less than that of your standard E cell. So the standard E cell is computed, reminding you, from this reduction table, so that you always have a constant standard E cell for a particular reaction. It's when you change up that concentration that will change up the overall cell voltage in the end. So what does a Q greater than 1 means? It means there are more products than reactants at non-standard conditions, because Q, reminding you, is a ratio of products over reactants. So if there's a high amount of Q, that means there's more products than reactants for us to have a large Q value. And that means that the reaction is probably going to be reversing itself to try to use up the products, to try to get back to equilibrium. A reverse shift is going to decrease the E cell because it's going the reverse direction. The forward shift is actually going to increase E cell. So it's making it less spontaneous in the forward direction. Now, unlike that, when you have E for this to be equivalent, the E cell non-standard and the standard, that means the ln is 1, or Q is 1. And that means ln of Q is 0, so the E cell are equivalent. This is when equilibrium is established, where both reactants and products are equally favored. So basically, your E cell is going to equal, your non-standard is equal to your standard conditions. Now, when you have a situation, and I'm going to erase this so we can see this next scenario. In this next scenario, your E, your Q is less than 1. Now, what would make it less than 1? Well, that means you're going to have a low Q. A low Q means there's low products and a lot of reactants. So where will this reaction want to go at these non-standard conditions? Well, it's going to want to shift to making more products to use up the excess reactants to reach equilibrium eventually. And so the forward shift will increase. Forward shift means the reaction is going to be more spontaneous in the forward direction, which means the E cell will be increased and more spontaneous in the forward direction. So E cell overall, now non-standard is going to be greater than the standard E cell of the reaction. So this is really important for us to understand using the Nernst equation, how this dynamic works for when Q is greater than 1, equal to 1, or less than 1. Let's go ahead and look at how this plays out in actual quantitative ways. So in example 8, we've got your line notation here. You've got your oxidized and your reduced on this side. So it's written without spectator ions right here, as you can see. And this is all at standard condition. So we're going to first calculate the cell potential at standard condition. To do so, I would suggest writing a reaction. The first thing you want to do is write a chemical reaction showing the reduction and oxidation. And how we're going to see this is because the format is what it is. This is your oxidation. So this is aluminum becoming aluminum 3+, as you see here. 3 electrons are going to be lost when aluminum becomes aluminum 3+. And so we write that half reaction. And looking at the reduction table, this is my standard reduction potential for the oxidation half reaction. Now we go to the cathode. Here's the cathode side. So it's iron 2+, gaining electrons to become solid iron here. And 2 electrons are gained for that to happen. Now we see that the electrons don't equalize, so we have to find a common multiple, and a common multiple is 6. So I'm going to multiply the top equation by 2, bottom equation by 3, and that will equalize the electrons. Thus, when we add them all together, your electrons cancels, leaving us with an overall voltage of 1.22 volts. So this is our E cell standard here, E cell standard for this reaction. Now, what happens if we take the same scenario and we change the concentrations such that it's no longer going to be standard, which is 1. Q is 1, which is when the concentrations are all 1 here. Now, be aware of something. It says right here, important. Notice that 0.5 molar is really 1 molar for aluminum because of the 2 right here. Multiplying that in, you get 1.0 molar. For every 1 mole of aluminum sulfate, there's 2 molar of aluminum 2+. So this is truly standard conditions, even though it doesn't look like it's 1 molar on both sides. It's because this gets multiplied in, giving us really 1 molar aluminum. So these standard conditions of 1 molar solutions now has changed up into different concentrations. So I know to use the Nernst equation, where I'm given different concentrations. Now it's still 1 molar here, but notice how it's not 1 molar here for the iron 2+ ions. So the first thing I want to do is, knowing my net equation, I want to set up my Q. My Q is always products over reactants, but excluding the solids. So I am going to make an effort to make sure I do not include my solids. So the Q in this equation, or the Q expression, is going to be products, which is aluminum 3+, raised to the second power, because it's a coefficient, over reactants raised to the third power, because of the coefficient. Now I can plug in my Q, in essence. I'm actually going to put in my, my values for N, or my R, my T, and my F. So temperature still stays at 298 Kelvin. R is 8.314. And then your Faraday's constant is 96,485. So when I multiply the R, T, and F and divide the F, I will get this value of 0.0592. And then I'm going to switch my ln to log. Now, once again, you can actually still put in whatever the original, you can put it in natural log form, but I decided to put it in log form. Well, let me go ahead and do it based on whatever equations you're given, okay? So my E cell, I want to make sure I'm consistent with what your equation sheet shows. So equation sheet shows this, and E standard. Now E standard was found to be 1.22 volts. Now I'm going to subtract the concentration, or my negative R, so 8.314 joules per mole times Kelvin, and then my T is 298 Kelvin. My N is the number of electrons transferred, which is 6 electrons transferred. And you're going, where did I get that? Well, notice I multiplied this in 6 electrons lost, 6 electrons gained. So that's where the 6 electrons comes from. And then I just substitute my Faraday's constant, which is 96,485. And then I do my ln of my Q. And my Q in this case is products, which is 0.01 raised, oh, my apologies, it's actually 1 molar. So let me go backwards. It's 1 molar raised to the second power, so that's aluminum's concentration. I'm putting in aluminum's concentration squared. Now I'm ready for iron 2+ concentration. That's why I really want to write this expression, so I know what I'm looking for and what to put where. So my iron 2+ concentration is 0.01, and it's raised to the third power. Now you will notice that this Q right here is going to be greater than 1. If it's going to be greater than 1, as we noted up here, greater than 1, you will expect the E cell non-standard is to be less than the E cell standard. So when you calculate all of this, and I'm going to pause so I can do all the calculations. It's going to take me a little longer or a little long to do so. So when I calculate everything and get the output, I should expect my E cell to be greater than 1.22 volts, which is my E standard. I get, as a result, 1.16 volts when I calculate using the Nernst equations with these non-standard concentrations for my ions in solution. Go ahead and do, once again, a way to conceptualize this, and oftentimes In this, AP doesn't require you to do the calculations. I am holding you to the calculations though. But to conceptualize this, and an appropriate answer would be what you see right here, where it describes how Q is greater than K at this point of the non-standard condition compared to the standard equilibrium condition. The E cell is less than the E standard because Q is greater than 1, which is means there's more products than reactants, indicating a reverse shift favoring the reactants. The reverse shift results in a decrease of the E non-standard cell value, and the reaction becomes less spontaneous in the forward direction. The same goes here in letter C. Now you have different concentrations of both the oxidation and the reduction, and so you're going to calculate it based on that. Remember that there's 2 moles here, so you're going to twice that to get the aluminum ions concentration, and here I have the value for it. And then the reactants would be right here. It's 1 molar. Substituting everything in, you'll notice that Q here is a really small number. So Q is much less than 1. With Q being less than 1, when you calculate your ln of Q, you'll find that the ln of Q is going to be a negative value here for this term. A negative value of a negative is going to give you a positive, which means you're going to add to the standard cell, which means your E cell is going to be greater than your E standard. So use that concept of understanding when ln is going to be a negative, ln of Q is going to be a negative versus positive value, to understand how the E cell ends up being even more spontaneous in the forward direction in the end. So it's Q less than K, and so the E cell is going to be more than the E cell standard because Q is less than 1, indicating there's going to be a thermodynamically favorable reaction towards the products, so the forward direction, and thus an increase in the E cell as a result. So yeah, calculate it and make sure you're familiar with that. This is just a different form of taking all the constants. When you multiply all the constants together, these constants right here for standard or for the same temperature or standard temperature as well as R and Faraday's constant, you end up with 0.0592, but also when you log, so you switch the ln to the log. So those are the 2 components that gives you, in the end, this value right here. You don't have to know this equation. You actually want to know the original Nernst equation. All right, your turn. Do FRQs from here on out. FRQ 2 and 3, you're practicing these electrochemical cells, leading into FRQ 4. In order not to be redundant, we did discuss this already, so we're going to move on to more FRQs and MCQs to work through. Moving into FRQ 5 and 6, FRQ 5 and 6 and 7, and then we get to electrolysis. So what is electrolysis? Electrolysis is now taking the second scenario, no longer a spontaneous reaction. We're actually taking a non-spontaneous reaction, and we're going to drive electricity through it continuously in order for that chemical reaction to occur. And to do that, we have to quantify the electricity Q as it passes a given time. And there's a website that I'd like you to explore to understand electrolysis in its basics. So we talked about Faraday's constant, and it's derived from the charge of each electron, where each electron's charge is 1.6 times 10 to the negative 19 coulombs for 1 mole for 1 electron. And we know a mole of electrons is 6.022 times 10 to the 23rd. So in multiplying the two, you get how much charge per 1 mole of electron. So this is called Faraday's constant. What we're going to look at is how we can take an electrolytic cell, or we can make an electrolytic cell by passing current through that. And in example 9, we're passing a certain amount of current. Now, current is I here, and it's in amps. And then what it does is current measures the rate of electrical flow. So you're seeing charge per time. So it's a rate. And that charge is the quantity of electricity, and time is in seconds. So we'll need Faraday's constant to help us maneuver through these calculations. So we have here a current of 0.452 amps passed through an electrolytic cell of molten calcium chloride for 1.5 hours. So we're going to first show the reaction of electrolyzing calcium chloride. And then we're going to quantify how much products are formed in the respective electrodes. So the first thing we want to do is take the reaction of calcium chloride and react it to form the products. And the products is going to be the decomposition of calcium chloride into calcium solid and chlorine gas. Now, what's this intermediate? This is really showing the oxidation numbers of each of the ions, which then changes in oxidation number when they become calcium, neutral calcium, and neutral chlorine. So I'm going to break it up into half reactions as we normally do. So the half reaction that we're seeing is, and let me assign oxidation numbers. This is +2, -1, 0, and 0. So I see calcium decreasing, so it's reduced. Calcium 2+ is reduced down to neutral calcium. So this is my cathode, which is where my reduction occurs. I'm gaining 2 electrons as a result of becoming neutral calcium. And then, of course, in this case, it's chloride ion becoming chlorine gas. And so you're seeing electrons lost. And so 2 electrons are lost. 1 electron is lost for each chloride ion. And now there's 2 of them, so there's 2 total electrons. Now, balancing this redox reaction, I get this resulting equation. That's why I ended up I wrote it as the broken up ions, because truly when you dissect the calcium chloride, these are the 2 ions that make up the calcium chloride. The voltage ends up being, when I calculate it, -4.23 volts. Now, a negative value for voltage means this reaction is in fact non-spontaneous. Recall the equation that links G to E, and that's -NF cell. So a negative value placed in here for the E cell is going to give me a positive G. So this is going to yield a positive G. And that positive G means the reaction is non-spontaneous. So now I take my equation that links current with charge, which is this I equals Q divided by T. Current being a rate of charge over time. That time has to be in seconds. So I want to calculate my charge, which is my Q. To do so is to take my current and multiply times my time. And my time is converted from hours to seconds. So it's a little simple side conversion, 1.5 hours. 1 hour has 60 minutes. 60 minutes is, or 1 minute has 60 seconds. And that will convert my hours into seconds. And when I do that conversion, I will get 5,400 seconds. So this is my time unit. This is my T. And I'm given current, which is 0.452 amps. Multiplying the two will give me my coulombs. Why do I want coulombs? because there I can then calculate stoichiometrically how much I have of my products forming, which is calcium. Or sorry, not stoichiometrically, stoichiometrically as well as dimensional analysis. So the first thing I want to do is I take my charge, and I know that there's 96,485. So I'm going to change that to a more precise value. 485 coulombs there is in a mole of electron. So that's how much charge in 1 mole of electron. Now, there's 2 moles of electron carried through in that electrolytic cell. So 2 moles for every 1 mole of calcium. And we saw that in the half reaction. If you remember, and the half reaction was this half reaction that we wrote in the chart earlier. And notice how 2 moles of electrons are passed or gained by the calcium 2+ ions for every 1 mole of calcium that's formed. So that's where I got the 1 mole of calcium right here, coefficient 1 to every 2 moles of electron. And then all I do from there is figure out how many grams of calcium for 1 mole of calcium, and that is how much calcium will form, given that you're running calcium chloride for 1.5 hours, and that's the formation of the amount of products formed. I would do this the same for the next instance. We're starting off with the same amount here of coulombs, and you're figuring out how much chlorine gas, and all you're doing is stoichiometrically right here, seeing how much, and then also dimensional analyzing or analyzing dimensionally the grams of chlorine gas. Again, I'm going to use Faraday's constant with a more precise value given, 485 coulombs, okay? 96,485 coulombs. What I want you to do is work through the next set of problems using this equation right here, which is how current is a function of charge per time unit. And you can figure out through each calculation. One of my recommendations is to write the reaction out so you can see how many moles of electrons are transferred between the substances. And so I'm going to set you up for this first one, and then you'll just work through the rest of the calculations. I went ahead and edited example 10 quite a bit because it actually didn't make sense to electrolyze a solution of silver nitrate. It would be water that ends up being electrolyzed. So I ended up saying zinc deposited for when you electrolyze molten zinc chloride. You'll understand why a solution of silver nitrate would not lead to the silver nitrate electrolyzing later on when we talk about setting up an electrolytic cell itself. So the first thing you want to do is write a reaction out, and the reaction is you're taking zinc chloride, solid, and you're electrolyzing it into zinc, solid, and chlorine gas. You should split up your half reactions and kind of figure out who is oxidized and who is reduced. So +2, -1, 0, and 0. And then when you split up your half reactions, you'll be able to see how many electrons are transferred. So zinc looks like it goes from a 2+ to a neutral charge, which means 2 electrons are gained from zinc. And then chloride ion goes from Cl- to Cl2, and there's 2 of them, so there's 2 electrons total loss. So you can see how many electrons are transferred per 1 mole of zinc in the end. And that's what you're trying to go after, is how many electrons are transferred for every mole of zinc. Starting off, we're using the equation for calculating charge. So you multiply your current times the time so you can find the charge. The charge will lead you to figuring out how many how much product is formed in the end. So I start off with multiplying my amps, which is 0.10 amps, times it by my time unit in seconds. So you can do a little side calculation. 10 minutes, 1 minute has 60 seconds, so that's 600 seconds. And that will give you your coulombs, your charge. And it looks like it's 60 coulombs in the end, because 1/10 of 600 is 60. And so you're going to take your 60 coulombs and you're going to convert those coulombs into moles of electrons. And then you go, and for every 2 moles of electrons transferred, there is 1 mole of zinc formed. And that's why the half reactions should be set up so you can see how many electrons are carried through. And 1 mole of zinc has a molar mass of 65.38 grams of zinc. And then when you multiply it out, you get 0.020 grams of zinc. So it's all dimensional analysis, pretty easy. Electrolytic cells and calculating electrolytic cells is all a matter of dimensional analysis with a bit of stoichiometry here. Go ahead and do example 11 and the challenge question down below. FRQ 8, work your way through. Do FRQ 9 and FRQ 10. And FRQ 11, moving into an electrolytic cell and how to set up an actual electrolytic cell. So let's talk. In example 12, you're electrolyzing molten sodium chloride. Now, molten sodium chloride means sodium chloride, which is usually a solid, is melted at a high temperature such that it becomes a liquid. And when you do that, what happens is you only have sodium chloride to deal with, and you're electrolyzing it to decompose the sodium chloride to form sodium solid and chlorine gas. When I separate it into half reactions, as you see right here, you'll notice that my E voltage is negative, so it's a non-spontaneous reaction. That's why you need to apply electricity. So that's why you're using electricity to break it up. Lysis means break up. When we set up this battery, or we set up this cell, electrolytic cell, what we have to do is we divide it up into knowing who our cathode, which is sodium ions on this side, and our anode, which is chloride ion. Now, you're oftentimes going to see this all submerged into one beaker. You're not seeing the half cells, the electrochemical half cells that you saw with the salt bridge. You're actually putting this all into the same beaker where you see molten sodium chloride. Now, what happens is the loss of electrons, which is the chlorine right here on this side. So chloride ion is going to be attracted to this side, causing us to bubble out chlorine gas. So you're seeing these bubbles are chlorine gas at the anode. So this is your anode side. Now this electrode is going to be inert, so it's not going to react at all. All you're seeing is the attraction of the chloride ions that is in sodium chloride, the molten sodium chloride, attracted to this inert electrode. And upon being attracted, you're going to gain an electron or lose an electron from this electrode by the chloride ion becoming chlorine gas. So electrons are going to be lost and then moved from this battery right here. So this battery is really driving these electrons over to the cathode end. In the cathode end, you're gaining an electron. The sodium ion is going to be attracted to this inert electrode where electrons are being delivered. Positive, negative, positive, negative is going to attract this electrode and gain an electron, accumulating sodium. So you're actually going to see sodium accumulating, sodium solid, so Na solid on this electrode. So you'll know which electrode is which because one electrode is bubbling chlorine gas. The other electrode is, you're going to see some growth of mass from the sodium solid. And the electrons are flowing between these two. And so you have a closed circuit allowing the electrons to flow from the cathode end, which is right here on this. The electrons are moving from the positive cathode in the battery to the negative anode in the battery here. And so that's what it describes, is the current flowing of the electrons from the cathode, positive end of the battery, to the anode, negative end of the battery. And this is electrolysis. Now, in example 13, on the other hand, this is still a non-spontaneous reaction, but you're electrolyzing water. And if we look at the electrolysis of water, what you're seeing is water becomes hydrogen gas and oxygen gas. And when that happens, you'll notice that this is a non-spontaneous reaction if you calculate the E voltage of this reaction. And so water, because it's non-spontaneous, you're going to need a battery to basically drive this reaction to occur for the decomposition of liquid water into the parts of hydrogen, 2 moles of hydrogen gas and 1 mole of oxygen gas. Okay, so I looked at the reduction table, and the cathode end, the reduction, the gaining of electrons, is going to occur with this half reaction right here. And what you're going to do is you'll notice hydrogen gas being formed from water because we're electrolyzing water. So you're looking for all the half reactions dealing with water for the electrolysis of water. And in that, I'll notice that there's a different number of electrons, so I'm going to have to double this reaction. Doubling this reaction leaves everything leading to this overall reaction in the end. And the voltage ends up being edited to negative 2.06 volts. And with a negative E voltage, you can see that this reaction is non-spontaneous. Thus, we need a battery. Now the question is, what is this dilute sulfuric acid? We need a medium because water, we know self-ionizes, but it's a very weak amphoteric substance, and so you need a pretty good electrolyte solution. So you need free ions, and you need something that is strongly or very soluble, which in this case is a strong acid like sulfuric acid, which allows the free flowing of the electrons between the anode to the cathode, and it creates this full circuit in the end. So that's why sulfuric acid is there. It provides it is the electrolyte solution that allows for the conductivity to occur between the cathode and the anode. Otherwise, you would not see the ability for the electrons to flow in a full circuit. I would like for you to take a little time to read this little story about the electrolysis of water. You'll notice also, again, the two half reactions. This is where the anode is, and so this side is the anode, and then this side is the cathode in the end, where the electrons are gained. And you also should look at the stoichiometry of this situation, where you'll notice hydrogen is going to be twice, because you're going to have to double this half reaction. It's going to be twice as much volume as the oxygen that you see forming here. And that's, how, again, how you know which one is the cathode versus the anode. The electrons, once again, always flow from the side where the anode is, so the loss of electrons, to the cathode. And notice in the battery, it's the positive, which is the cathode end, to the anode end of the battery itself. So this is what's, when we talk about the battery, it is the flow of electrons always in electrolysis goes from the positive end of the battery to the negative end, which is where the anode is going to the cathode in the end. Read this and make sure you understand it in the end. And then we'll go into electrolysis. Now, if you have, instead of molten salt, so it's not just pure salt, now you have water in there, what happens is the reaction leads to electrolysis of water once again. And when you have electrolysis of water, and the question is, why are you not seeing the salt part be involved in the redox reaction? And that's because when you have an ion like sodium ion trying to become sodium solid, that's actually an implausible reaction, because sodium really wants to lose its electron, not gain an electron. We found what would lose an electron. We have to find something to gain that electron, and this reaction is impossible, if not implausible. So the other substance would be the hydrogen ion gaining those electrons to become hydrogen gas. And depending on whether you're in an acidic or basic solution, you'll use one half reaction versus the other. And that's why your voltage is either negative 1.23 volts or 2.06 volts if it's in a basic solution. So, but the better, oftentimes, more often than not, you're going to notice it's this half reaction. So I'm going to star it as knowing that this is the reaction you'll often see when it comes to electrolysis of water. So in the end, the word aqueous is going to be very essential to knowing that electrolysis of aqueous sodium sulfate is going to lead to the electrolysis of water. Now, what role does this sodium sulfate serve as? Well, it's a very soluble salt, so it serves as our electrolyte to allow the conductivity or the flow of our electrons between the anode to the cathode. All right, go ahead and work through example 12 and then lead into the rest of the FRQs ending this unit. FRQ 13, FRQ 14, FRQ 15, and then the MCQs leading it into your AP set problems.